Hello, settle in, get comfortable, and prepare for a journey to the very edge of our known universe. Have you ever gazed into the night sky and wondered what lies beyond the last visible star? What secret is hidden past the event horizon of our universe? Most of us picture an infinite void, or perhaps just more of the same, galaxies, stars, and nebulae scattered uniformly into eternity. But what if I told you that at the very edge of the observable cosmos, a place that should, by all accounts, be homogeneous and predictable, scientists have found something? Something so colossal that its mere existence shatters our most fundamental understanding of the structure of the cosmos. This is a structure that, according to our best theories, simply should not exist. Tonight's sleep lecture is dedicated to this cosmic monster. We will travel 10 billion light-years from Earth to examine the Hercules-Corona Borealis Great Wall, an anomaly forcing astrophysicists worldwide to revisit the very foundations of cosmology. Prepare to learn how this incredible finding was made, why it calls into question everything we thought we knew about the universe, and what fantastical theories are being proposed to explain its nature. This is the story of how one look into the deep cosmos can change everything. Before we zoom toward the most mysterious structure in the universe, let's first map out our journey. We need to understand the world we inhabit according to current scientific understanding. Picture the universe. It is vast, almost incomprehensible, but scientists rely on one crucial principle to make sense of it, the cosmological principle. It sounds complex, but its core idea is simple. This principle dictates that when viewed on a sufficiently grand scale, the universe looks roughly the same in every direction and from every location. In other words, it is homogeneous and isotropic. There is no special center or designated edge. Travel billions of light-years in any direction, and the overall pattern remains consistent. Clusters of galaxies separated by immense voids. Think of a sponge. Up close, you see a complex structure of walls and holes, but from a distance, it appears to be a uniform material. This is exactly how scientists pictured our universe at the larger scales. This idea forms the foundation of nearly all our cosmological models, including the Big Bang theory. For a long time, all observations confirmed this principle. Astronomers found structures like superclusters of galaxies forming what we call the cosmic web, but there was believed to be an absolute limit to their size. This calculated limit sits at roughly 1.2 billion light-years. Any structure larger than that simply would not have had enough time to form over the universe's 13.8 billion-year existence. This was an unshakable law, a boundary scientific thought dared not cross, and it is against this backdrop, a world governed by order and homogeneity, that our main character emerges, a structure whose very existence laughs in the face of that limit. Our journey into the greatest mysteries of the cosmos begins not with powerful telescopes peering into the blackness, but with the most fierce and luminous events in the universe, gamma-ray bursts. Picture a colossal star, many times more massive than our own sun, that has finally run out of fuel. It collapses under the weight of its own gravity, triggering a burst of unimaginable power in a single instant. In those few seconds, it releases as much energy as our sun will emit over its entire 10 billion-year lifespan. This blinding beam of gamma radiation slices through the void, traveling across billions of light-years to finally reach our detectors here on Earth. These events, known as gamma-ray bursts, are the brightest electromagnetic phenomena known to humanity. They are so incredibly powerful that we can observe them from the absolute furthest reaches of the observable universe. For astronomers, they serve as cosmic lighthouses. By studying them, we can peer back in time and witness the universe when it was still much younger. In the early 2000s, several space observatories, including NASA's SWIFT satellite and the Italian-Dutch Beppo-Sachs satellite, tirelessly scanned the heavens, recording these distant flares. Their primary mission was to study the bursts themselves, their causes and consequences. But a team of astronomers led by István Horváth from the National University of Public Service in Budapest decided to use this data for an entirely different purpose. Their idea was simple, yet brilliant. If gamma-ray bursts occur when massive stars die, and those massive stars are born inside galaxies, then mapping the distribution of GRBs could effectively provide a map of matter distribution in the most remote parts of the universe. They began collecting the data like cosmic cartographers, plotting every flare on a three-dimensional map of the sky. Each gamma-ray burst represented a single dot, indicating the presence of a distant galaxy. Year after year, their map grew increasingly detailed. They expected to see exactly what the cosmological principle predicted, a smooth, random distribution of dots spread evenly across the celestial sphere. But as the data accumulated, they started noticing something strange. In one specific area of the sky, toward the constellations Hercules and Corona Borealis, the dots began to clump together. This was no random coincidence. The bursts were lining up, forming a colossal arc that stretched across an unbelievably vast section of the heavens. Initially, they were highly skeptical. Perhaps it was a data error or a systematic instrumental bias. They double-checked their calculations, analyzed the telescope performance, and searched for any potential terrestrial or technical explanation for this anomaly. Yet the more data they analyzed, the clearer the picture became. The anomaly wouldn't disappear. In fact, it grew increasingly statistically significant. There, 10 billion light-years away, nestled within the young universe, was a colossal structure, a massive clump of matter that, according to established theory, simply shouldn't exist. This was the first hint of a discovery that would shake the foundations of modern cosmology and force us to question just how well we truly understand our universe. So, what exactly did Istvan Horvath's team discover on their map of gamma-ray bursts? Imagine looking up at the night sky. It appears to us as a sphere, but in reality, it's a window into three-dimensional space, and perhaps more crucially, a window into the past. Light from distant objects travels for billions of years before it reaches us. The region that grabbed the scientists' attention covered an enormous patch of sky. Initially, it was just a group of 14 gamma-ray bursts that were all located roughly the same distance from us, between 9 and 10 billion light-years, and clustered tightly together in one specific region. Statistical analysis revealed that the probability of such a concentration occurring purely by chance was extremely low, less than 0.01%. This was intriguing enough, but the true magnitude of the challenge to standard cosmology only became apparent when the scientists estimated the structure's sheer size. It stretched roughly 10 billion light-years in length. Let's pause for a moment and try to grasp the enormity of that number. Our own galaxy, the Milky Way, is only about 100,000 light-years across. The distance to the nearest major galaxy, Andromeda, is 2.5 million light-years. The largest structure known to us until this point, the Sloan Great Wall, measured about 1.4 billion light-years long and was already considered a cosmic giant. The new structure was almost 7 times bigger. It is so vast that light would need 10 billion years just to cross it from one end to the other. This duration is comparable to the age of the universe itself, which stands at 13.8 billion years. If you could travel at the speed of light and started your journey from one edge of this structure at the moment of the Big Bang, you still wouldn't have reached the other end even now. This structure occupies more than 10% of the diameter of the entire observable universe. Picture a world map. Now imagine a single country on that map that covers 1/10 of the Earth's total surface area. It isn't just a country, it's an entire continent whose existence nobody had ever suspected. The scientists named their discovery the Hercules-Corona Borealis Great Wall, after the constellations in whose direction it is observed. This is not a solid wall in the literal sense of the word. Rather, it is a gigantic thread or filament within the cosmic web, a gravitationally bound complex made up of galaxy superclusters, gas, and presumably dark matter. We only see its brightest points, the galaxies where the gamma-ray bursts originated. But these points, like the tips of an iceberg, indicate the existence of something far more massive and extended, hidden in the depths of the cosmos. The discovery of this structure was like ancient cartographers who drew dragons off the edges of the known world, suddenly finding an entirely new world beyond those edges, a world that didn't fit any of their existing geographical models. This wasn't just a new detail on the map of the universe, it was a detail that compelled scientists to discard the map altogether and start drawing it again fresh, wondering what other unimaginable behemoths might be lurking in the uncharted oceans of space. Why is the existence of the Hercules-Corona Borealis Great Wall such a colossal problem for science? To grasp this, we need to revisit the cosmological principle we discussed earlier. This principle of homogeneity and isotropy isn't just a beautiful philosophical idea, it's the bedrock upon which the entire edifice of modern cosmology is built. It is baked into Einstein's equations of general relativity, which govern the evolution of the universe. According to these equations and the Big Bang theory, the universe began in an extremely hot and dense state. In the first moments after the explosion, tiny quantum fluctuations existed, microscopic differences in density. As the universe expanded and cooled over time, gravity began to amplify these fluctuations. Where the density was slightly higher, matter started aggregating, forming the seeds of future galaxies and clusters. Where the density was slightly lower, voids formed. This process is comparable to water droplets merging on a foggy window pane, forming larger drops and streams. Computer simulations based on this model beautifully reproduce the universe we observe, a cosmic web of filaments and walls surrounding vast, empty voids. But these simulations have one critical limitation. The rate at which these structures can grow is restricted by the speed of light and the expansion rate of the universe. Over the 13.8 billion years of the universe's existence, there simply hasn't been enough time, physically, for a structure larger than roughly 1.2 billion light-years to form. The gravitational influence from one end of such a giant structure couldn't travel fast enough to the other end to pull them together. This theoretical maximum is what scientists called the end of greatness. It was believed that on scales exceeding this limit, the universe must become smooth and homogeneous, like that piece of sponge viewed from far away. Now imagine the Hercules-Corona Borealis Great Wall, a structure 10 billion light-years across, smashing into this elegant picture. It is 7 or 8 times larger than the theoretical maximum allowed. This is like finding a 10-kilometer tall tree or a million-ton animal here on Earth. This isn't just an anomaly, it is a direct and violent breach of a fundamental principle. Its existence implies that either our understanding of how structures formed after the Big Bang is fundamentally flawed, or the Big Bang theory itself, along with the cosmological principle, requires serious revision. This is a challenge thrown at the entirety of modern cosmology. If this wall is real, it means that some processes we are completely unaware of were, or are, active in the universe. Perhaps matter in the early universe wasn't distributed as smoothly as we assumed, or maybe there were some exotic, unknown mechanisms that allowed these structures to grow much faster than physically possible under current models. This calls everything into question, from our grasp of gravity to our ideas about the very first seconds after the universe was born. The Great Wall is not just an object, it is a question the universe has posed to itself. And the answer could fundamentally redefine our view of reality. When faced with such a shocking discovery, the scientific community naturally reacted with a heavy dose of skepticism. In science, extraordinary claims require extraordinary evidence. The very idea that a structure 10 billion light-years across could actually exist was so radical that the first priority was to rule out all possible errors and alternative, less exotic explanations. The primary source of doubt centered on the detection method itself. To reiterate, the wall wasn't found through direct observation of galaxies, but rather by analyzing the distribution of gamma-ray bursts. Gamma-ray bursts are rare and random events. We only see those that occur in galaxies along our line of sight, and crucially, only those whose relativistic jets happen to be pointed precisely at Earth. This means we are observing just a tiny fraction of the total bursts. Critics argued that the observed clustering might simply be a statistical anomaly, a trick of chance. Perhaps we were just lucky to spot several bursts in one direction, while equally numerous bursts in other areas of the sky simply missed us. This is analogous to looking down at a city at night from space and seeing several bright searchlights grouped together. You might assume there's a massive stadium below, but they could just as easily be several randomly placed billboards. Another major point raised by skeptics involved potential observational bias. Our instruments aren't perfect. Space telescopes that register gamma-ray bursts have varying sensitivities across different areas of the sky. Perhaps in the direction of the Hercules and Corona Borealis constellations, the Swift telescope was for some reason more sensitive, or maybe it was affected by background noise, leading to a spurious increase in the number of recorded events. The scientists who made the discovery, of course, accounted for these factors. They ran sophisticated statistical tests to prove that their result was not the result of chance or error. They partitioned the sky into different sections, compared the distributions, and showed that the observed concentration of bursts was highly, statistically, significant. But the debate raged on. Some researchers even suggested that the suitability of gamma-ray bursts as indicators of matter distribution might be overstated. Perhaps the conditions necessary to produce these powerful explosions are more common in specific types of galaxies or regions with particular chemical compositions, and that, rather than overall matter density, is what creates the appearance of structure. This scientific dispute continues to this day. The Hercules-Corona Borealis Great Wall sits in a kind of scientific limbo. On the one hand, there is compelling data suggesting its existence. On the other hand, the detection method is not entirely reliable, and many scientists are taking a wait-and-see approach, demanding confirmation through other observational techniques. For instance, by deeply scanning that region of the sky specifically for the galaxies themselves, not just the bursts within them. This is a normal, healthy process in science. Before we rewrite the textbooks, we need to be absolutely certain we are not looking at a mirage. Yet it is precisely these controversial and puzzling discoveries that push science forward, forcing us to seek out new methods and formulate new theories. Let's assume for a moment that the skeptics are wrong and the Hercules-Corona Borealis Great Wall actually exists. If so, what could have possibly created this cosmic leviathan? What exotic forces were at work in the early universe to gather such a colossal amount of matter, seemingly defying all known laws of physics? One of the most intriguing and debated hypotheses is the theory of cosmic strings. To understand what these are, we need to return to the very first moments after the Big Bang. The universe was incredibly hot and dense, existing, according to physicists, in a state of high symmetry. As it expanded and cooled, it underwent what are called phase transitions, similar to how water turns into ice when it freezes. When water freezes, ice crystals begin to grow from different points and in different directions. When these growing crystals meet, defects form at the boundaries where they touch, cracks in the ice structure. Theory predicts that something similar might have happened in the early universe. As it cooled, various fields permeating space-time froze into their minimum energy states. And if these fields froze differently in different regions of space, defects could arise at their boundaries. These defects aren't cracks in the traditional sense, they are exotic objects. Depending on the type of phase transition, different kinds of defect could form. Point defects like magnetic monopoles, two-dimensional defects, domain walls, and most interesting for us, one-dimensional defects, cosmic strings. A cosmic string is a hypothetical, unimaginably thin line of energy, possessing colossal mass and tension that could stretch across vast distances, perhaps even the entire observable universe. It is thinner than a proton, yet just 1 centimeter of this string might weigh as much as Mount Everest. If they exist, these strings would have formed in the first second after the Big Bang and survived to the present day. What do they have to do with our Great Wall? Everything. Cosmic strings possess enormous gravity. They could act as gravitational seeds. Sweeping through the early universe, such a string would have attracted surrounding matter, gas, dust, and dark matter, forcing it to clump along its path. Over billions of years, a giant filament of galaxies and clusters could have grown along this primordial string, far exceeding the size limits allowed by the standard model. Thus, the Hercules-Corona Borealis Great Wall might be nothing more than a shadow cast by one of these ancient cosmic relics. We wouldn't see the string itself, but we would see its gravitational consequence, the colossal cluster of galaxies it assembled around it. This theory is extremely elegant because it explains not only the wall's massive size, but also its elongated filamentary shape. Furthermore, the existence of cosmic strings is predicted by certain versions of string theory and other grand unified theories which attempt to unify all the fundamental forces of nature. Finding confirmation of their existence would represent a monumental breakthrough in physics. For now, cosmic strings remain purely hypothetical objects. Scientists are actively searching for them, for example, by analyzing the cosmic microwave background radiation or looking for specific gravitational lensing effects, but convincing evidence remains elusive. However, if the Great Wall is real, it could become the first and strongest piece of evidence that these exotic threads in the fabric of space-time truly exist. If the cosmic string hypothesis sounds too exotic, buckle up. We are about to dive into concepts that are truly mind-bending. What if the Hercules-Corona Borealis Great Wall isn't just an object within our universe, but a sign that something far grander exists beyond it? What if this immense structure is a scar or an imprint left behind by an interaction with another realm? This line of reasoning catapults us straight into one of the most staggering ideas in modern physics, the multiverse theory. The notion that our universe is not singular but merely one of an infinite collection of universes, all nested within a colossal multiverse, has long been debated by physicists and philosophers alike. Several versions of this theory exist. For instance, the theory of eternal inflation suggests that the Big Bang which birthed our world was not a solitary event. Cosmic inflation, the period of hyper-rapid expansion in the universe's first moments, might be happening perpetually, generating new bubble universes constantly. Each of these bubbles would expand, oblivious to the existence of its neighbors, potentially possessing unique laws of physics. But what if two of these bubbles in the distant past collided or simply brushed past one another? Such an event would leave an indelible mark. The gravitational influence from a neighboring universe could impose a massive imprint on ours, causing large-scale density fluctuations in matter. The Hercules-Corona Borealis Great Wall might be exactly that, a cosmic bruise, or scar, from a multiversal fender bender that occurred billions of years ago. This gigantic accumulation of matter could have formed along the line of gravitational distortion left by the passing universe. Another version of this idea stems from string theory, or more specifically, its extension known as M-theory. In this model, our three-dimensional universe is envisioned as a membrane, or a brane, floating within a higher dimensional space called the bulk, or hyperspace. This hyperspace could host other branes, other parallel universes. Normally, these branes do not interact. However, M-theory allows for the possibility of a collision. Such an event would be catastrophic, perhaps even triggering a new Big Bang. But even if the branes only passed closely, their gravitational interaction would leave a residual trace. The Great Wall, in this view, might be the spot where our brane universe was gravitationally dented by a passing neighbor. Of course, this sounds like pure science fiction. We currently have no direct proof of other universes. These concepts exist on the extreme frontier of theoretical physics and are highly speculative. Experimentally verifying them is incredibly difficult, if not outright impossible. However, they are compelling because they offer a potential explanation for phenomena that simply do not fit into the standard cosmological model. If we observe a structure in our universe that could not have formed through internal processes, it is logical to hypothesize an external influence. And what could be a more powerful external influence than an entire other universe? Thus, by staring at this distant cluster of gamma-ray bursts, we may be looking at the first indirect evidence of the multiverse itself. It is a concept that is simultaneously terrifying and mesmerizing. It suggests that our world is far larger and more complex than we have ever dared to imagine. Let's take a step back from the wildest theories and examine how the Great Wall fits into our existing understanding of the universe, though perhaps with a few modifications. We know that the visible matter, stars, gas, and dust, makes up only about 5% of the total mass energy of the universe. Roughly 27% is attributed to mysterious dark matter, and 68% to the even more enigmatic dark energy. The key to understanding this gigantic structure may very well lie within these dark components. Dark matter is an invisible substance that neither emits nor absorbs light, revealing itself only through gravitational influence. It is widely considered the primary sculptor of the universe's large-scale structure. Clumps of dark matter formed in the early universe created deep gravitational wells. Ordinary baryonic matter then flowed into these wells, ultimately forming galaxies and their clusters. The cosmic web we observe is essentially a visible framework built upon an invisible foundation of dark matter. What if the Hercules-Corona Borealis Great Wall is simply an exceptionally large and dense filament within this dark matter web? Perhaps for some reason, the primordial density fluctuations in this region of space were abnormally high. This would have led to the formation of a colossal filament that subsequently attracted a massive amount of ordinary matter. In this scenario, we wouldn't need exotic objects like cosmic strings or collisions with other universes. We remain within the standard cosmological model, but we are forced to admit that it allows for far more extreme fluctuations than we previously assumed. This raises a new question. What could have caused such giant primordial fluctuations? The answer might be tied to processes that occurred during the epoch of inflation, the hyperfast expansion of the universe in the first fraction of a second of its existence. Perhaps inflation wasn't as smooth and homogeneous as generally believed, leaving behind a few scars in the form of regions with anomalously high density. On the other hand, there is dark energy, the mysterious force driving the accelerated expansion of the universe. Its nature remains one of physics' greatest enigmas. We don't know if it is a constant cosmological parameter, as Einstein hypothesized, or if its density changes over time. Dark energy opposes gravity. It stretches space, preventing structures from growing. However, if in the past, when the universe was younger and denser, the influence of dark energy was weaker than it is today, this would have given gravity more time and opportunity to form super-large structures. Thus, studying the Great Wall could provide a key to understanding the nature of dark energy itself. If we can prove that such structures are indeed possible to form, we will have to reassess our models of cosmic evolution and potentially redefine the balance between gravity and dark energy. The Great Wall could be a gigantic cosmic dynamometer measuring the strength of these fundamental components of our reality. This illustrates how a single anomaly can be linked to the deepest mysteries of cosmology. In trying to explain it, we are forced to touch upon everything, from the nature of dark matter to the evolution of dark energy and the very earliest moments of the universe's existence. What future awaits the mystery of the Hercules-Corona Borealis Great Wall? How can we definitively confirm or debunk its existence and, if confirmed, truly understand its nature? The answer lies in the next generation of telescopes and observational programs, tools poised to revolutionize our view of the cosmos. The main issue with our current data, as we've discussed, is its indirect nature. We infer the wall's presence from the distribution of gamma-ray bursts, not from the direct observation of the galaxies that comprise it. To truly settle this debate, we need powerful telescopes to conduct a deep, detailed survey of this specific region of the sky. Our objective is to create a three-dimensional map of the galaxy distribution in that area to see if they genuinely form a super-dense structure. This is a truly Herculean task. We are talking about a region of the sky stretching billions of light-years away. Galaxies at this distance are incredibly faint. Seeing them and accurately measuring their distance, which is crucial to confirm they are part of the same structure rather than just randomly projected onto the same patch of sky, requires hundreds, if not thousands, of hours of precious observing time on the world's largest telescopes. Great hope rests on new observatories. The James Webb Space Telescope, JWST for instance, with its unprecedented infrared sensitivity, is designed to peer into the most distant and dust-obscured corners of the early universe. It could potentially see through the presumed wall and resolve the faint galaxies that populate it. Another key instrument is the European Space Agency's Euclid telescope, specifically built to map the universe's large-scale structure. Its primary goal is to study dark energy and dark matter by precisely measuring the distribution of billions of galaxies. While its main survey may not cover the entire Great Wall region, Its data will help us better understand the maximum size of structures fundamentally possible in the cosmos. Back on Earth, the Vera C. Rubin Observatory in Chile is preparing for operation. This telescope will conduct a decade-long survey of the entire southern sky, creating the deepest and most detailed movie of the universe ever made. Its data will map billions of galaxies, giving us the statistical power needed to search for and study other extremely large structures. If the Hercules-Corona Borealis Great Wall is real, similar, albeit perhaps smaller, structures should exist elsewhere. Future sky surveys will either find them, confirming that our universe is not as uniform as previously believed, or they will show that the wall is a singular anomaly, deepening the mystery even further. Moreover, we anticipate progress in the study of gravitational waves and the cosmic microwave background, CMB. If the wall was formed by cosmic strings, these strings might have left specific imprints on the polarization of the CMB, or they could be the source of a gravitational wave background noise. Future gravitational wave detectors, like LISA, may be sensitive enough to capture these faint signals from the early universe. We are standing on the cusp of a new era in cosmology. The Great Wall mystery presents one of the greatest challenges to our current models, and the tools to meet this challenge are already being built. Perhaps within the next 10 to 20 years, we will finally have the answer. And whatever that answer is, it will fundamentally change our understanding of the cosmos forever. Let's take another look at the very core of this issue, the cosmological principle. For almost a century, it has served as the guiding beacon for cosmologists. The notion that the universe, on vast scales, looks the same everywhere and in every direction was not just elegant, it was incredibly practical. It allowed scientists to build relatively straightforward mathematical models of the entire cosmos without needing to map the location of every single galaxy cluster. Think of it this way. A climatologist can model Earth's climate without having to factor in the specific weather of every single city. Models derived from this principle were tremendously successful. They accurately predicted the expansion of the universe, the existence of the cosmic microwave background, the echo of the Big Bang, and the precise ratio of light elements, like hydrogen and helium, that formed in the cosmos's infancy. All these predictions were brilliantly validated by observation. It truly seemed we had finally found the right framework for understanding the universe. Yet, as is often the case in science, nature turned out to be far more complex and fascinating than our neat models allowed. The Hercules-Corona Borealis Great Wall isn't the first crack in the foundation of the cosmological principle, but it is certainly the most profound. Even before this discovery, astronomers had found other structures that seemed to push beyond the theoretical limit. For example, in 2003, the Sloan Great Wall was identified, spanning nearly 1.5 billion light-years. Then, in 2013, came the huge LQG, or Huge Large Quasar Group, a cluster of 73 quasars roughly 4 billion light-years across. Each of these finds ignited fierce debates within the scientific community. Defenders of the Standard Model insisted these were merely statistical outliers, the biggest possible perhaps, but still consistent with the overall picture of random fluctuations. Their analogy was this: if you flip a coin enough times, eventually you'll get 100 heads in a row. That doesn't violate the laws of probability, it's simply a rare event. But with the discovery of the Hercules-Corona Borealis Wall, which dwarfs the previous record holders, that argument is starting to wear thin. This isn't 100 heads in a row, it's 1,000. At a certain point, you have to concede that perhaps the coin is rigged. What if the universe truly isn't homogeneous on the very largest scales? What if our observable 93 billion light-year diameter bubble is simply a tiny and potentially atypical slice of a much larger meta-universe? Perhaps we reside in a region of anomalously high density, while other areas might be far more desolate, or conversely even more structured. If we are forced to abandon the cosmological principle, the consequences would be immense. It would mean our current models of the universe are just local approximations, and we cannot confidently extrapolate our findings across the cosmos as a whole. This complicates everything: our estimations of the universe's age, its composition, and its ultimate future. This would be nothing short of a Copernican revolution. Back then, we accepted that Earth was not the center of the universe. Now we may have to accept that our region of the universe isn't typical either. It's a terrifying yet exhilarating thought. It opens the door to entirely new ideas and theories. Perhaps this Great Wall is the key to a deeper understanding of our true place in the cosmos. To truly grasp how revolutionary the discovery of the Great Wall is, let's take a brief journey through the history of mapping the universe. For millennia, humanity's map of the cosmos was two-dimensional. Ancient astronomers charted stars and constellations onto celestial atlases, imagining them as simple points affixed to a crystalline sphere. The breakthrough arrived in the early 20th century when scientists like Vesto Slipher and Edwin Hubble learned to measure the distances to those distant nebulae. They realized these were, in fact, other galaxies, islands of stars similar to our own Milky Way. The universe gained its third dimension, depth. The map of the cosmos officially became three-dimensional. By the mid-20th century, astronomers began the first systematic sky surveys, attempting to chart the locations of thousands of galaxies on this new three-dimensional framework. The initial results were astonishing. Galaxies were not scattered randomly, they were clustered into groups and vast superclusters. Our own galaxy, the Milky Way, was found to be part of the so-called local group, which itself was an outlying member of the gigantic Virgo supercluster. Then in the 1980s, Margaret Geller and John Hotra, conducting a galaxy redshift survey, made one of the greatest discoveries in modern cosmology. They uncovered the CFA2 Great Wall. This was a gigantic, flattened structure made up of thousands of galaxies, stretching 500 million light-years across. For the first time, it became clear that the universe possessed a structure resembling a sponge or soap bubbles, composed of flat walls and elongated filaments surrounding huge, practically empty regions known as voids. This monumental finding launched an entire sub-discipline of astronomy, cosmography, or the mapping of large-scale structure. Other massive surveys followed: the 2-degree Field Galaxy Redshift Survey, or 2DF, and the Sloan Digital Sky Survey, or SDSS, mapped millions of galaxies, revealing the cosmic web in all its splendor. It was within the SDSS data in 2003 that the Sloan Great Wall was discovered. At the time, it became the largest known object in the universe, spanning 1.4 billion light-years. Each of these discoveries pushed the boundaries of the known, but they all generally fit within the constraints of the standard cosmological model. In fact, many scientists believed the Sloan Great Wall represented the end of greatness, the theoretical maximum size for a structure that could possibly form. And yet, against this backdrop, after decades of meticulous mapping, the Hercules-Corona Borealis Great Wall emerged. It wasn't just slightly larger than the previous record holder, it was 7 times bigger. This wasn't just another incremental step in knowledge, it was a leap into an entirely new category. Compared to this monster structure, all the previous Great Walls suddenly look like small fences. This discovery proves that the history of mapping the universe is far from complete. We thought we had already sketched out the major continents on our map and only needed to refine the coastlines. Instead, it turns out we may still be navigating a small bay with a whole new, unexplored ocean awaiting us beyond the horizon, an ocean filled with islands and continents of unimaginable size. It serves as a profound reminder of humility. The universe will always find a way to surprise us, and the most breathtaking discoveries might still lie ahead. To truly grasp its scale, let's try to visualize this colossal structure. Imagine our Milky Way galaxy, a disk of hundreds of billions of stars, spanning 100,000 light-years across. Now shrink it down to the size of a single grain of sand. At this scale, Andromeda, our nearest major galaxy, would be another grain of sand sitting about 2.5 centimeters away. The Virgo supercluster, which holds thousands of these grains of sand, would be a sphere roughly 1 meter in diameter. Now, in this exact same visualization, try to picture the Hercules-Corona Borealis Great Wall. It would be a filament of these grains of sand and spheres, stretching out for 10 kilometers. 10 kilometers! This structure is so immense compared to our galaxy that the ratio is like comparing the size of a single person to the distance across an entire continent. Here is another analogy. The observable universe spans about 93 billion light-years. Let's compress that entire observable universe down to the size of Earth. At this scale, our own Milky Way galaxy would be smaller than an atom. And the Hercules-Corona Borealis Great Wall, it would be a structure stretching from North America to Europe like some kind of colossal undersea mountain range. It is crucial to understand that this is not a solid, monolithic wall. It is not a brick structure. Instead, it is a gravitationally bound complex made up of superclusters of galaxies, which are themselves clusters of galaxy clusters. Running between these superclusters are gigantic filaments of hot gas and presumably dark matter. Even within the wall, the individual galaxies are separated by millions of light-years of sheer vacuum. Nevertheless, the density of matter inside this structure is far higher than the universal average. If we could travel through it on a spaceship, we wouldn't observe a random distribution of galaxies, but rather a distinct concentration flowing along a defined direction. We would fly past one dense supercluster after another, a journey that, even if we were traveling near the speed of light, would take us 10 billion years. Another astonishing fact concerns its age, or more specifically, the epoch in which we are observing it. The light from this structure has been traveling for 10 billion years to reach us. This means we are seeing it as it existed when the universe itself was only 3.8 billion years old. It already existed in this gargantuan form during a time when our own solar system hadn't even begun to coalesce. This makes its very existence even more baffling. Gravity had far less time available to pull this behemoth together. It's like finding a fully constructed modern skyscraper in a photograph from the 19th century. This doesn't just challenge the known laws of physics, it fundamentally violates our understanding of cosmic timescales and the speed of structural formation. Visualizing these scales helps us move past the dry statistics and truly internalize the profound depth and strangeness of this discovery. This structure challenges not only our theories but also the limits of our imagination. It serves as a potent reminder that space is where reality can often turn out to be far more fantastic than anything we could possibly invent. How is it even possible that such a colossal structure went unnoticed for so long? Astronomers have been diligently scanning the skies for decades, armed with increasingly powerful instruments. The answer lies in several key factors. First, there's the sheer distance. 10 billion light-years puts it right at the very edge of the observable universe. Galaxies that far away are incredibly faint. Their light is severely attenuated and stretched due to the expansion of the cosmos, a phenomenon known as redshift. To map out the structure and pinpoint the location of the individual galaxies that form the wall, you need the most advanced telescopes and extremely long exposure times. Most sky surveys simply lack the depth to peer that far and in such detail. Secondly, consider its massive size across the sky. The Great Wall spans an angle of more than 70 degrees. This is a truly enormous stretch. For comparison, the full moon takes up only half a degree. That means the wall is 140 times wider than the visible disk of the moon. No single telescope can capture an area that large in one shot. To map it, researchers had to create a mosaic stitched together from thousands of individual images. This demands colossal resources and immense observation time. Because of this difficulty, most astronomical research focuses on smaller, deeper sections of the sky, hoping to find something interesting there. The idea of deliberately searching for a structure of this gargantuan size simply hadn't occurred to many scientists because it actually contradicted existing cosmological theory. Thirdly, and critically as we mentioned earlier, its discovery was only made possible through a non-standard technique, using gamma-ray bursts, or GRBs, as indicators. Traditional methods for finding large-scale structures rely on painstakingly mapping the galaxies themselves. This is reliable but slow and labor-intensive, especially over vast distances. Gamma-ray bursts, being incredibly luminous, are visible from extreme distances and allow us to instantaneously probe the universe to enormous depths. This was essentially a scientific life hack that revealed something hidden from conventional methodology. In a way, the Great Wall was hiding in plain sight. Its component parts, individual distant galaxies, almost certainly appeared in countless astronomical images, but nobody could assemble those scattered points into a coherent single picture until the right tool and the right idea came along. This is a highly instructive story about the importance of not just new technology in science, but also novel approaches and a willingness to think outside the box. Sometimes, to see the forest, you have to stop looking at the individual trees and rise above, utilizing a fresh, unexpected perspective. In this case, gamma-ray bursts served as the perfect satellite that allowed us to finally see the full cosmic picture and trace the contours of this previously unseen continent in space. Let's turn back to the alternative explanations and examine them more closely. Could the Great Wall simply be an optical illusion, a kind of cosmic mirage? One such hypothesis involves gravitational lensing. According to Einstein's general theory of relativity, massive objects, like clusters of galaxies, warp the fabric of space-time around them. Light from more distant objects passing near this lens gets deflected and distorted. This can result in us seeing a distant object magnified, duplicated, or even stretched out into an arc. Now imagine that between us and the distant universe, where these gamma-ray bursts originate, there are several extremely massive yet invisible clusters of dark matter. They could act as a complex system of lenses and mirrors, distorting the actual distribution of the bursts. It's possible that the bursts are actually distributed uniformly, but these gravitational lenses focus their light from different regions into a single point on our sky, creating the illusion of an ultra-dense clustering. This idea is intriguing, but it has inherent problems. To create the illusion of a structure 10 billion light-years across requires a highly specific and unlikely configuration of gravitational lenses. Furthermore, gravitational lensing typically introduces characteristic distortions in the images of objects, which we should be able to detect through detailed analysis. So far, no such distortions linked to the gamma-ray bursts have been found. Another possibility, as we've already mentioned, isn't an illusion, but what's known as selection bias. Perhaps we see more gamma-ray bursts in that specific direction, not because there are more galaxies overall, but because there are more galaxies of a specific type where these bursts occur more frequently. For instance, it's known that the long gamma-ray bursts used in the study are tied to the collapse and death of extremely massive stars. These stars don't live long and are primarily found in galaxies experiencing active star formation and possessing low metallicity, meaning they have a low concentration of elements heavier than hydrogen and helium. What if the Great Wall is less of a matter cluster and more of a river of primordial gas, where conditions for the formation of these specific stars were particularly favorable during that epoch? In this scenario, the overall density of matter might not be abnormally high, but it's highlighted for us by a large number of gamma-ray bursts. This hypothesis seems more plausible and is harder to disprove without additional data. To test it, we would again need to conduct a direct survey of the galaxies in that region. We must check whether low metallicity and high star formation rate galaxies truly predominate there. If that proves true, the mystery of the Great Wall will shift from a cosmological problem to an astrophysical one. It will cease being a challenge to fundamental principles and become an interesting, yet explainable feature of galaxy evolution. However, if the galaxies turn out to be ordinary, just far more numerous than expected, then we revert back to the original dilemma, a violation of the cosmological principle. This is precisely why future observations are so crucial. They must help us distinguish between an illusion or systematic error and a genuine, shocking reality. What if the cosmological principle simply doesn't hold true? Let's imagine we live in a universe where homogeneity and isotropy break down. What would that world look like, and what would it mean for us? If the universe isn't uniform on the largest scales, it implies regions exist with dramatically different characteristics. Our observable bubble might just be one of many provinces in a colossal meta-universe. Perhaps we are residing in a cosmic metropolis, an ultra-dense region where galaxies are packed tightly together. Meanwhile, billions of light-years away, vast cosmic deserts might stretch out, where matter density is thousands of times lower and galaxies are incredibly rare. Conversely, maybe our neighborhood is the quiet cosmic backwater, and structures like the Hercules-Corona Borealis Great Wall are just the outskirts of the true center of the world, where density and structure are even more profound. In such a non-uniform universe, the fundamental cosmological parameters we measure might not be universal, they could be purely local. Take, for instance, the Hubble constant, which describes the universe's expansion rate. We measure it by observing the galaxies around us, but if we live in an overdense region, local gravitational attraction might slightly slow down the expansion. In emptier voids, the universe might expand faster. This variation, incidentally, could potentially resolve one of modern cosmology's major headaches, the Hubble tension, where values measured by different methods slightly disagree. Perhaps the reason they don't match is precisely because they are measuring the expansion rate in different locations and at different epochs. Furthermore, if the universe were anisotropic, meaning its properties depend on direction, the implications would be equally profound. Physical laws or fundamental constants might subtly differ depending on which way you look. While this sounds like scientific heresy, some researchers are already hunting for such anomalies, perhaps in the fine structure of distant quasar spectra. So far, however, no convincing evidence has emerged. Life in such a non-uniform universe would be far less predictable. We couldn't be certain that the laws we've discovered in our lab, 93 billion light-years wide, would hold true in other unreachable domains. This raises fundamental questions about the very nature of science and the limits of our knowledge. Our cosmic situation would be comparable to that of an ancient islander. They've explored their island thoroughly, knowing every stone and tree, believing they understand the laws of nature. But they don't know that across the ocean lie other continents with different flora, fauna, and perhaps even different climates. The Hercules-Corona Borealis Great Wall could be that distant, barely visible shore on the horizon, the hint telling this islander that their world is far larger and more diverse than they ever imagined. This perspective forces us to be humbler in our claims of fully understanding the cosmos. It demands that we be ready for the most incredible discoveries just around the next corner, discoveries that could force us to reevaluate everything we currently hold as truth. When we discuss exotic theories, such as cosmic strings or multiverses, it's crucial to understand they aren't just scientists indulging in flights of fancy. These ideas emerge at the very forefront of theoretical physics, born from serious attempts to solve the deepest mysteries in our understanding of the world. Let's delve a bit deeper into where these concepts originate. The theory of cosmic strings, for instance, is a natural consequence of many grand unified theory, or GUT, models. For decades, physicists have dreamed of creating a single, unified theory that describes the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, as different aspects of one single underlying force. It's believed that in the ultra-high energy conditions of the early universe, these forces were truly indistinguishable. As the cosmos cooled, this symmetry spontaneously broke, and the forces effectively froze out or separated from one another. As we've mentioned before, such phase transitions could have generated topological defects, with cosmic strings being one possible example. Therefore, if grand unified theories hold true, the existence of cosmic strings is practically unavoidable, and if the Great Wall anomaly turns out to be their relic signature, it provides powerful, indirect evidence for this entire grand physical picture. It truly links the world of massive galactic structures with the realm of subatomic particles and fundamental forces. As for the multiverse, that idea also rests on solid theoretical foundations. The concept of the inflationary multiverse, for example, springs directly from the theory of cosmic inflation, which is currently the best explanation for many large-scale properties of our universe, such as its flatness and uniformity. Yes, the very uniformity that the Great Wall seems to challenge. According to the theory, once inflation begins, it may never completely stop everywhere. It ceases in isolated regions, creating bubble universes like our own, but continues unabated in the space between them, stretching that area and perpetually giving rise to new universes. This scenario, known as eternal inflation, is simply a natural mathematical consequence of the equations describing the process. Another version, the string theory multiverse, is also not arbitrary speculation. For string theory to be mathematically consistent, it requires the existence of additional hidden spatial dimensions. The geometry of these hidden dimensions can vary, and each possible geometric configuration, a number estimated to be as high as 10 to the power of 500, could correspond to a separate universe, each possessing its own unique set of physical laws and constants. Our universe is merely one possibility within this vast, infinite landscape of options. Of course, all of this remains firmly in the realm of mathematics and hypotheses for now. The core problem is that these theories operate at energy levels and scales currently unreachable by our experiments. We cannot build a particle accelerator powerful enough to verify grand unified theories, nor can we peer into another universe directly. This is precisely why cosmology serves as our unique laboratory. Anomalies like the Great Wall might be the only window we have into this world of new physics. They could be the fossilized remains, allowing us to reconstruct the appearance of the dinosaurs that lived during the exotic epoch of the early universe. That is what makes their study so exciting and critically important. Let's pose another crucial question. How do the various giant structures we've discovered in the universe relate to one another? Is the Hercules-Corona Borealis Great Wall a unique anomaly, or is it simply a piece of some much larger global structure that we are only now beginning to recognize? We've already mentioned the Sloan Great Wall and the huge, large quasar group, or huge LQG. But there are other contenders for the title of ultra-large structures. Consider, for example, the GRB ring, a ring-shaped formation of 9 gamma-ray bursts spanning more than 5 billion light-years in diameter, or the Laniakea supercluster, which our own galaxy is a part of, a gravitationally bound region over 500 million light-years across. All these objects demonstrate that the universe, on scales ranging from hundreds of millions to several billion light-years, possesses an extremely complex hierarchical structure. Galaxies cluster into groups, groups form clusters, clusters form superclusters, and these superclusters line up into filaments and walls, creating the cosmic web. The standard model of cosmology generally describes this hierarchy well, but only up to a certain limit. The Hercules-Corona Borealis Great Wall defies this conventional picture by being an order of magnitude larger than everything else. One intriguing possibility is that all these structures might be interconnected. Perhaps the cosmic web has not just one, but multiple levels of hierarchy. What we previously considered to be the largest filaments might actually be thin fibers woven into much thicker ropes. The Great Wall could be one of these cosmic ropes, with other giant structures acting as its constituent parts or adjacent, less pronounced formations. This idea leads us to the concept of the so-called fractal universe. A fractal is a self-similar structure that looks the same regardless of the scale at which you view it. Imagine a snowflake. Each point on the snowflake replicates the general shape of the whole, and each tiny branch replicates the shape of the main point. During the 1970s and 80s, some cosmologists proposed that the universe might be organized according to fractal principles. The distribution of galaxies within a cluster would resemble the distribution of clusters within a supercluster, and so on, ad infinitum. In such a universe, there would be no upper limit on the size of structures, and the cosmological principle would fail. However, later and more precise observations, such as those from the Sloan Digital Sky Survey, suggested otherwise. On scales exceeding several hundred million light-years, the fractal structure appeared to break down and the universe became homogeneous. But the discovery of the Great Wall forces us to revisit this idea, albeit in a modified form. Perhaps the universe isn't strictly fractal, but it certainly isn't entirely uniform either. It's possible that discrete levels of hierarchy exist, and we have just stumbled upon a new, uppermost layer. This would imply that our cosmos is far more complex than we once imagined. It's not merely a uniform sponge, but a sophisticated, multi-layered construction whose rules we have yet to fully grasp. And every new ultrastructure we discover serves as another piece of this gigantic cosmic puzzle we are striving to solve. What impact does the discovery of the Great Wall and the resulting debates have on the scientists themselves, on the human aspect of science? It serves as a perfect illustration of the scientific process in action. It's not a smooth, linear path from ignorance to knowledge, but rather a turbulent journey, rife with arguments and contradictions. On one side, you have the team of scientists who made the discovery. They are convinced they are right. They have conducted numerous tests and published their findings in peer-reviewed journals. To them, the Great Wall is a reality that demands explanation. They likely feel like pioneers, having looked beyond the horizon and witnessed something that will change our understanding of the world. They are ready to defend their position at conferences, in papers, and in heated debates with colleagues. On the other side is the scientific community, which is inherently conservative. And this is a good thing. Science should not accept every sensational claim at face value. Its role is to question, test, and retest. Skeptics don't necessarily want to disprove the finding. They want assurance that it is robust. They point out weaknesses in the methodology, suggest alternative explanations, and demand new, independent verification. This process can be frustrating for the initial discoverers, but it is absolutely vital for the health of science. It acts as a crucial filter, weeding out errors, chance coincidences, and hasty conclusions, allowing only the most reliable and verified facts to pass through. Between these two poles sits the majority of scientists who are taking a wait-and-see approach. They acknowledge that the discovery is intriguing and that it hints at a potential problem within the standard model, but they are not ready to rewrite the textbooks until stronger evidence emerges. They follow the discussion closely, await new data, and perhaps are planning future observations themselves that might shed light on this enigma. This story also highlights the vital role of interdisciplinarity in modern science. The initial finding was made by observational astrophysicists, but to explain it, we need theoreticians working in cosmology, particle physics, and string theory. We need statisticians to assess the data's reliability and engineers to build newer, more sophisticated telescopes. The mystery of the Great Wall is unifying the efforts of hundreds of people from widely different scientific disciplines. And naturally, discoveries like this generate tremendous interest among the general public. They capture our imagination, forcing us to contemplate the most fundamental questions. How is the universe structured? Are we alone? What lies beyond the known? They demonstrate that science is not a collection of dry facts in a textbook, but a living, thrilling adventure full of mystery and unexpected turns. Even if it ultimately turns out that the Great Wall is a statistical artifact, the sheer act of debating it has already yielded enormous benefits, compelling scientists to re-examine their models and develop new methods for testing the cosmological principle. Let's try to peer into the truly distant future. What is the ultimate fate of colossal structures like the Hercules-Corona Borealis Great Wall in an ever-expanding universe? Our cosmos, it seems, is headed for a cold and lonely old age. Dark energy, that mysterious force pushing galaxies apart, will only grow more dominant over time. Even now, distant galaxies are receding from us at speeds exceeding the speed of light. This doesn't violate the theory of relativity, because space itself is expanding. This acceleration means we live in a universe defined by an event horizon. Light from galaxies beyond this boundary will never be able to reach us. As the expansion accelerates, this horizon will creep closer and closer. The galaxies we see today will vanish behind it one after another. In 100 billion years, an observer in our galaxy will only be able to see the galaxies of our local group, which are gravitationally bound and won't scatter apart. All other galaxies will vanish from sight, their light stretched so far by expansion that it becomes entirely invisible. The universe beyond our small island group will become utterly black and void. But what about the Great Wall itself? It too cannot eternally resist the all-conquering force of dark energy. While the superclusters within it are gravitationally bound, the overall structure most likely is not. The sheer scale, 10 billion light-years across, is simply too vast for gravity to hold it together as a single entity. Consequently, the accelerating expansion of space will slowly but surely tear it apart. The superclusters that compose the wall will begin drifting away from each other, eventually receding beyond the cosmic horizon. Trillions of years from now, no trace of this monumental structure will remain. It will simply dissolve into the expanding emptiness. This is a rather melancholic prospect. We currently live in a unique cosmological epoch. We appeared late enough for galaxies and stars to have formed, yet early enough to still witness the remnants of the Big Bang and the grand architecture of the cosmos. Future civilizations, should they arise trillions of years hence, will inhabit an entirely different world. They will only see their immediate group of galaxies and will assume that this small collection constitutes the entirety of existence. They will never know about the Big Bang, or the cosmic microwave background radiation, or the vast cosmic web, or the Hercules-Corona Borealis Great Wall. Knowledge of our true origins and the majestic scale of the cosmos will be lost to them forever. This places a special responsibility upon us as a civilization. We are witnesses to the golden age of cosmology. We must gather as much information about our universe as possible before it hides itself behind a veil of eternal darkness. Every new discovery, every map of the universe we create is a message in a bottle we leave for the distant future, a testament to what our universe truly looked like in its young and tumultuous epoch. As we conclude our journey, let's take a moment to reflect on the philosophical significance of this discovery. What does it truly tell us about our place in the universe and the very nature of knowledge itself? Throughout human history, we have strived to find order in the surrounding world. We sought simple, elegant laws capable of describing the immense diversity of phenomena. The cosmological principle was the pinnacle of this endeavor. It offered us a comfortable, predictable view of the universe, a place devoid of chaos, where the same rules apply everywhere, and where our little corner is no better or worse than any other. The Hercules-Corona Borealis Great Wall ruthlessly shatters this idyll. It reminds us that the universe is under no obligation to conform to our notions of simplicity and order. It can be strange, asymmetric, riddled with anomalies and exceptions. It was not designed to be easily understood. This discovery teaches us intellectual humility. We are often tempted to believe that our current theories represent the final truth, the ultimate pinnacle of creation. Yet the history of science shows that every final theory eventually proves to be just an approximation, a stepping stone toward a deeper understanding. Newton's theory was replaced by Einstein's, not because Newton was fundamentally wrong, but because his theory only operated within certain limits. Perhaps our own standard cosmological model, founded on the cosmological principle, is also just an approximation, one that works well on small scales, say a few billion light years, but breaks down the moment we look further afield. The Great Wall is a finger pointing toward the boundaries of our current knowledge. It tells us, here, past this line, the unknown begins. Your old maps are useless here. It is time for new ideas and new breakthroughs. This is not a cause for dismay. Quite the opposite. It is a cause for excitement. The most boring thing that could happen in science is if we discovered everything and answered every question. Mystery and enigma are the fuel that drives scientific progress, and the Great Wall stands as one of the greatest mysteries confronting modern cosmology. It guarantees that the next generation of astronomers and physicists will have plenty of fascinating work ahead of them. Finally, this discovery forces us to re-examine the sheer grandeur and scale of the cosmos. We live on a tiny planet orbiting an unremarkable star, nestled within one of hundreds of billions of galaxies. And this reality of ours is only a part of a structure that is itself a mere detail in an even more immense design, a design whose dimensions and nature defy our imagination. This feeling of insignificance in the face of the universe can be frightening, but it is also profoundly inspiring. It liberates us from petty, earthly concerns and reminds us that we are part of something truly vast and wondrous, and we have the unique opportunity, even if only for the brief moment of our existence, to touch these great mysteries and attempt to unravel them. And so our long, quiet journey to the very edge of the observable universe is drawing to a close. We watched as the random flashes of distant, dying stars coalesced into a portrait of something truly incredible. We encountered a structure so vast it defied existence itself. The Hercules-Corona Borealis Great Wall isn't just a cluster of galaxies, it is a direct challenge to everything we thought we knew about the cosmos. It calls into question the fundamental principle of uniformity, the bedrock upon which 20th century cosmology was built. It forces us to consider the wildest, most fantastic ideas, from Big Bang relics like cosmic strings to scars left behind by collisions with parallel universes. Perhaps it's merely a statistical mirage, a trick of chance, or an observational error. Or perhaps, just perhaps, it is the first real evidence that our universe is far more complex, varied, and mysterious than we ever dared to imagine. Now that's a twist, isn't it? We thought we had drawn the final map of the world only to discover a whole new continent hidden just beyond its charted borders. This story is a perfect illustration of how science truly operates. It doesn't fear anomalies, quite the opposite. It seeks them out because it is exactly these mysteries, these wrong objects like the Great Wall, that propel us forward, forcing us to forge new theories and make groundbreaking discoveries. Thank you for spending this time with me, delving into one of the greatest mysteries of modern science. I hope this journey has been not only informative, but also calming. If you enjoyed it, please support the channel. Hit the like button, subscribe, and ring that notification bell so you don't miss new sleep lectures on the secrets of the universe. And now, before you drift off completely, I want to ask you a question. Let me know in the comments which theory explaining the nature of the Great Wall seems most plausible to you, or perhaps simply the most beautiful. Is it cosmic strings, the multiverse, or something else entirely? Good night, and may your dreams be clear and full of distant worlds.